Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. I'm going to take a look at computing arc length, again in sort of the setting of, say, a Calc 2 course. In a previous video, I showed you where the arc length formula came from, so just as a reminder, if I have the graph of a function of the following form, say y equal to f of x, and I'm looking at the length on the interval from a to b, then the arc length L is given by the integral from a to b, square root of 1 plus the square of the derivative dx. And again, that formula right there is not necessarily intuitive. However, if you look at the previous video where I posted sort of the derivation of this, you will see where all those things came from. Why is it a derivative? Why is it a square of a derivative? Why is it 1 plus that? Why is it under the radical? So all those things are illustrated in the previous video where I showed you where the formula came from. In this current video, I want to show you how to compute one of these. So let's say, for example, I have the function f of x is equal to 2 over the square root of 3 x to the 3 halves. And I want to compute the arc length on the interval from, let's say, 0 to 4. Okay. Now, first and foremost, before I get into the example, notice that we have to pick some very specific examples of functions that are actually going to work with this formula. I mean, if I pick, say x squared, right? Just something as simplistic as just x squared. The derivative would be 2x, and then the square of the derivative would be 4x squared, so I'd have the square root of 1 plus 4x squared. And unless you've done, say, trig substitution, that wouldn't be pretty much impossible to compute. Which, generally speaking, in your Calc 2 course, or in any Calc 2 course, you are going to learn trig sub, but you'll learn this formula first. So we have to pick some very specific examples that would end up working in this, right? Not many functions have an elementary antiderivative when I plug it into this formula. But this one will. Let's go ahead and see how this works. So solution. All right. The arc length is going to be the integral from 0 to 4 of the square root of 1 plus, again, the square of the derivative dx. All right, so let's go ahead and plug things in. This would be 0 to 4, the square root of 1 plus. All right, so let's differentiate that. So using the power rule, this would be 2 over root 3. The exponent comes down, so 3 halves. X to the, right, and using the power rule, the exponent reduces by 1. So 3 halves minus 1 would be 1 half. So there's the derivative, which will simplify a little bit, right? We can multiply those coefficients, and then after we do that, we'll square it, dx. All right, I get the integral from 0 to 4, square root of 1 plus 2 and 2 would cancel, 3 over root 3 leaves a factor of root 3 on top, so I have root 3 x to the 1 half, that whole thing squared, dx, and this gives me integral from 0 to 4, square root of 1 plus. Now if I square that, of course this is a product, so I square each factor. Root 3 squared is 3, square root, remember 1 half power is square root, so x to the 1 half squared would be x, therefore this term becomes 3x dx. All right, and if you want, you can use a u substitution on this, so let's go ahead and do that. All right, so I would have u is the inside function, so 1 plus 3x. My differential with respect to the variable u, this would be 3 dx. And let's also change the limits of integration, right? So the original limits of integration are related to the original variable x. But if I'm going to switch to the variable u, we have to switch those as well. To switch those, we think of this as a function, u as a function of x, and these are the x values. So to find the corresponding u values, we simply plug those in. U evaluated at 0 is going to be, of course, 1 plus 3 times 0, which is 1, and then u evaluated at 4 would be 1 plus 3 times 4, which would be 13. So for my integral with respect to u, my limits of integration will be 1 and 13. All right. Now also notice that in order to plug this in, I have a dx, but I don't have a 3 dx. So what I can do is I can put a factor of 3, and then I can cancel it by putting a factor of 1/3 out front. Now that integral is in the form for which I can plug all these things in, and I get the following. 1/3 integral from 1 to 13, and then remember 3 dx is my new du, and the square root of 1 plus 3x would be the square root of u. All right. And then in order to integrate a radical function, we usually turn it into an exponent, meaning I have 1/3 integral from 1 to 13 of u to the 1/2 du. All right. Antiderivative power rule says the exponent increases by 1, and then I divide by that increased exponent, which gives me 1/3 u to the 3/2 divided by 3/2, and then we'll evaluate that from 1 to 13. All right. Well, 1/3 divided by 3/2, if I'm dividing those fractions, we can flip and multiply. So 1/3 multiplied by 2/3. And then u, actually, let me just plug in the limits of integration here. Then it would be 13 to the 3/2 minus 1 to the 3/2, which gives me 2/9. 13 to the 3/2 doesn't reduce in any way, but this one will to at least 1, and we get that value right there. So certainly we could just pop that into a calculator, get a decimal approximation for it, but this right here would be the exact length of this curve on this interval. Thank you for watching. Please consider subscribing.